Okay, so let's go through test 3 for fall 2020 for all those you cats and kitties who can't make it to class right now. So, just a heads up, the useful information sheet includes only the periodic table, the Pauling electronegativity table, and a solubility chart, as there is no equations to really use. So anything you may need, please include that on whatever cheat sheet. Start off, draw a valid Lewis structure. Big key is valid. Doesn't have to be best, valid. So chlorine group 7 has 7 electrons. Plus 6 from oxygen, and there's double that, and plus 1 because it's charged is at 20 electrons. We slap our chlorine in the center, followed by 2 oxygens around it. We're down to 16. We put 6 lone pairs on each oxygen to give them 8. That leaves us, we've used 12, leave 4 left. We have to put them on the chlorine. This is the key thing. We have to use up all the electrons before we make any double bonds. Is this a valid Lewis structure? Yes, I could be done. However, if I wanted to lower the amount of formal charges, I would take one of these and swing it into a double bond. Yes, that would give the chlorine an expanded octet, but it is allowed because it is group 3. But our top structure is satisfactory, so we do not need to do that. Okay. Either of those would be okay. Hybridization. We need to be able to draw the Lewis structure to do this. So Br, 7 from Br, 7 from fluorine. All these are group 7. 7 times 3. Sometimes these 21. We have 28 electrons. Now, this doesn't have to be pretty. It just has to have all the things coming off of it. So 3 fluorines. That uses up 6. We're down to 22. We must then put 6 on each atom. That's 18. So we're down to 4. We have to slap those on the bromine. So now to get hybridization, we are looking at how many unique electron domains do we have coming off the bromine. We have here 1, 2, 3, 4, and 5. 5 total things coming off the bromine means we need 5 electron domains, 5 hybrid orbitals. So 1 from S, 3 from P, 1 from D. There's our 5. Now here, we need to check the activity chart. We need to see which metal will replace which metal solution. So you should have a reaction that looks like this if it were to occur. But so the rule is every metal that's higher on this activity chart will react with any and replace any metal that is lower on this activity chart. We have magnesium right here and lead right here. The question is lead higher than magnesium? No. So the answer is no. Now we have to look at gold. Gold right on the bottom. Is gold, square that, is that higher than cobalt? The answer is also no. Is cadmium, which is right here, is that higher than copper? Yes. Yes, that is. And is aluminum way up here, is that higher than silver way down here? And the answer is yes. So the answer is no, no, yes, yes. But so you're looking at which metal is higher than which other metal. Now, formal charges. Going down to the formal charges. How do we do formal charges? Formal charges, we look at the valence electrons and compare them to the actual electrons observed. So actual electrons, we're going to use half of all bonds and all lone pairs. So we have 1, 2, 3, 4 actual electrons for carbon. And carbon is group 4. So 4 minus 4, how many? What's the formal charge on carbon? 0. What about nitrogen? Nitrogen, atom 2. Nitrogen is group 5, yet we see 1, 2, 3, 4. So 5 minus 4 puts us at positive 1. And nitrogen 3, also group 5, count 1, 2, 3, 4, 5, 6. Each lone pair counts as 2 because they're fully on the atom as opposed to being shared. So our answer is 0, plus 1, minus 1. What is the molecular geometry of radon tetrachloride? Well, radon is a noble gas, so it's 8 electrons. And chlorine is group 7. So 7 times 4 is 28. 28 plus 8 is 36. Radon will be our central atom. So slap our 4 chlorines around it. That uses up 8. So we're down to 28. And we put our 6 electrons on each chlorine to give them an octet. So that right there is 24. We have 4 electrons left. We have to put them on the radon. So how many electron domains do we count? Count 1, 2, 3, 4, 5, 6. So that is 6 electron domains, which is the electron geometry of octahedral. However, I'm asking for the molecular geometry. Molecular geometry, we have to differentiate the bonds, 4 bonds, from 2 lone pairs. So 2 lone pairs means instead of octahedral, we are looking at square planar. Square planar is the shape. Page 2. So we start off on a good note with a typo. It should actually read manganese MnO4 minus. You could do it with MnO4 neutral, but what I was going for is MnO4 minus. So the charge of all the metal and the oxygen will have to add up to -1. Well, if each oxygen is -2, then Mn plus, -8 equals -1. So the only charge that manganese could have would be +7. Now, if you look at the periodic table, manganese is in group 7b. That is not a coincidence that 7b and 7 is our answer, though that will not always be the case. Now looking at this, so the first thing we need is the full equation written out. And BaSO4. And the reaction goes to BaCO3 and Na2SO4. To go beyond here, what do we have to do now? Now we would have to consult our solubility chart. So here's our barium. Here's our sodium. Here's our carbonate. Here's our sulfate. So based on this chart and this chart alone, we have this base, this space, this space. So wherever there is a black smart, it is a solid. Wherever it's clear, it is aqueous. So putting our labels on, we have aqueous, solid, solid, aqueous. Wherever there is aqueous, we're going to split apart, and the coefficients of the normally monoatomic ions would go up front, and the oxy ions would stay together. The polyatomics would stay together. So this would split into 2Na plus, carbonate 2 minus, all these aqueous. The solid would stay together. This solid would stay together, BaCO3, and would split to 2Na plus, aqueous, and SO4 2 minus, aqueous. From that point, the net ionic equation is we cancel out everything that appears identically on both sides. So you'd be left with carbonate plus barium sulfate equals barium, yields barium carbonate and sulfate. That would be how you would do that one based on the chart. Now, sigma and pi is very easy. Sigma is essentially every single bond, every initial bond. We count all the bonds once. Every initial bond is a sigma. The pi is a secondary bond. Pi, when we have a double bond is going to be 1 sigma and then 1 pi. A triple bond is going to be 1 sigma and 2 pi. So to do this, you simply have to count all the bonds once. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So every initial bond is a sigma. So I've crossed out every bond, at least every bond between every atom once. Any bonds remaining must be counted as our pi. So we have pi 1, we have pi 2, we have a pi 3. So we have 3 pi. That's how you can easily do sigma and pi. Don't overlook this. This is relatively simple if you know what to do. Valid Lewis structure for S2. Another simple one. S2. So we have 6 times 2, we have 12. We'll call 1 sulfur the center atom and 1 sulfur the outer atom. We're down 10. Put 6 electrons on the outer atom. Place remaining electrons on the inner atom. Now, we must make an octet by transferring electrons. So this has 2, 4, 6. We're going to take 1 lone pair and make this a double bond. That is a valid Lewis structure. 2, 4, 6, 8. 2, 4, 6, 8. There's a valid Lewis structure for sulfur. Okay, looking at this combustion reaction, every combustion reaction yields CO2 and H2O so long as it's burning some sort of hydrocarbon. To balance this, I'm going to start with this as 1, and I always want to balance the carbon and hydrogen first. Well, there's 3 carbon, so I'm going to put a 3 here. There's 8 hydrogen, but this is H2O, so this has to be 4. Now at this point, I can balance the oxygen. 3 times 2 is 6. 4 times 1 is 4. We have 10 oxygen on the right, so I must have 5 times 2 is 10 on the left. And lastly, classify the following reactions as combination, decomposition, single displacement, or double displacement. Combination is when two atoms become one, two compounds become one. Decomposition is the opposite. One compound breaks down into two. Single displacement is an element and a compound swap places, and a double displacement is a swap of two compounds. So this one, A plus B combines together form A and B. This is a combination. If you were to classify this as a type of reaction, this would also be a redox, because we have a pure element and a compound going into a compound, meaning this goes from 0 to something that's not 0. And that means there's another redox partner within that. So iron is going from 2 plus to 3 plus, oxygen is going from 0 to -2. This one, cadmium nitrate and magnesium sulfate, goes to magnesium nitrate and cadmium sulfate. So that is a double displacement. Cadmium and the magnesium are swapping places. Now, is this normally you would have to say, is this a precipitation type reaction? But if we look, cadmium sulfate right here and magnesium sulfate right there, this is actually no reaction, not a true reaction. There's not a precipitation that occurs. So, but still, it's written as a double displacement. Now, this guy, I'm going to rewrite this guy to better see this. But Na plus, Na neutral, and HOH, which is our water, they're swapping places. So this is a single displacement as this goes to hydrogen gas. So this is a classic single displacement, and because of that, it's also a redox, because every single displacement ends up with being a redox. Lastly, C6H5OH and lithium hydroxide these guys are swapping places. This is a double displacement again. But this would be considered an acid base, because a acid plus a base go together to form water and a salt. That is pages 1 and 2. Now we must draw a polar version of SF4Cl2. SF4Cl2. This is the only time you really need to focus on having the wedges and the dashes. So let's draw the Lewis structure first, just to make sure. Though the fact that there is 4 of these and 2 of these are a pretty good hint. However, because we've only learned how to draw 6 electron domains, and so there's 6 atoms, so it has to be octahedral. But let's check. S is 6. 7 times 4 is 28, plus 7 times 2 is 14. We have 48 electrons to place. So let's just draw a crappy Lewis structure. S, F, 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 Cl, Cl. That uses 2, 4, 6, 8, 10, 12. We're down to 36. We're going to put lone pairs on all the atoms. So 6, 12, 4, 12, 18, 24, 30, and 36. That leaves us with 0 electrons left to place. How many things are coming off it? 1, 2, 3, 4, 5, 6. 6 electron domains means this is octahedral. The base octahedral shape includes wedges and dashes. Now, if I were to put chloride up here, there's only one place the other chloride and get this wrong, and that would be below. To have a polar compound, if you have a symmetrical shape, you need unequal opposite atoms. So if I put a chloride here, those two chlorides would cancel out. All the fluorines would cancel out, and you'd be left with a nonpolar molecule. So I'm going to just put the chloride right here. And so long as I put the fluorines everywhere else, you're good. So even though this guy and this guy cancel out, we have a dipole pulling down. We also have a dipole pulling front left. So the net dipole ends up pulling down into the front left. But I'm not asking you to draw the dipoles on there. But the plus goes towards the less electronegative atom. The arrow goes towards the more electronegative atom. Okay, keep moving. Electron geometry of SO4 2 minus. 6 from sulfur, 6 from each oxygen, times 4 is 24, plus 2 minus. 24, 30, 32. Slap the sulfur in the middle, 4 oxygens around it. There's 8. We're back down to 24. We put 6 electrons on each oxygen. That gives us 24. We're out of electrons. Is this a valid Lewis structure? Yes. Is it good enough to get our answer? Yes. If we made double bonds to any of these oxygens, would it be a better Lewis structure? Yes. But if I made double bonds to any of these oxygens, would it change my answer? The answer is no. No, it would not change my answer. So how many things are coming off the sulfur? 1, 2, 3, 4. 4 electron domains. The electron geometry for 4 electron domains is tetrahedral. So that is our answer. Okay, moving on. Net ionic equation for this one. HClO4, strong acid. CSOH, a strong base. Reacts to form strong acid plus base always forms water and a salt. Now the solubility chart is a lot less helpful, but note that every time you have H2O, it is a liquid. It doesn't make sense for H2O to be aqueous. So, yeah. Looking at here, the only one you could really even look at is, there's no H plus, is cesium hydroxide or cesium perchlorate, but there is no cesium. However, with perchlorate, you'll notice nothing is insoluble for perchlorate. And rule 1 says any of these group 1 metals are also always soluble. So, meaning this guy's going to be aqueous, this guy's going to be aqueous, and this guy's going to be aqueous. So when I split this apart, I'm going to end up canceling out the cesium, canceling out the chlorate. Our net ionic equation for any strong acid and strong base is H plus and OH minus, aqueous, goes to water, liquid. That's the driving force for any acid-base reaction. Now, moving right along to my resonance structures. Which one of these guys has more than one resonance structure? You need either a double bond 2 atoms away or a lone pair 1 atom away from resonance from a double bond. So putting in the proper amount of lone pairs to these structures will help us. So now looking at this, we have a lone pair able to swing in here, make a triple bond, kicking that lone pair out. So resonance structure. Yes. We have a lone pair able to swing in, and they'll kick that double bond out. Resonance structure. Yes. Now we have no lone pairs here. However, if I swing this guy down, I'll kick this guy out. And kick that guy out and keep kicking. They're taking each other's places. Everything is swapped over. Everything is swapped over. So does this have resonance structure? Oh, yes. So all of these have resonance structures. Okay, moving right on. Net ionic again. Zinc nitrate and KCl. I'm going to go ahead and pre-balance this for us. It's going to give us KNO3 and zinc chloride. Now, going back to our solubility chart, here's our zinc. Here's our chloride. Here's our nitrate. Potassium nitrate, potassium chloride, both soluble. Zinc nitrate, zinc chloride, both soluble. Okay, well, if everything is soluble, everything is aqueous. If everything is aqueous, when they split apart, everything ends up canceling out. Two nitrates cancels two nitrates. Two potassiums cancel two potassiums. Two chlorides cancel two chlorides. One zinc cancels one zinc. We have no reaction. If everything is aqueous, there's no liquids, there's no solids, it is a no reaction. No reaction. What is the electronic geometry of Bf3? Boron is 3, group 3. Fluorine is 7. 7 times 3 is 21. We have 24 electrons. B, we put in the center. F, 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 that's 6. We're down to 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. We're out of electrons. While boron has less than an octet, that is allowed. However, if you did something crazy and move that into a double bond, would this change my answer? No. How many electron domains does boron have? 1, 2, 3. What would the answer have to be then? Trigonal planar. Trigonal planar. Draw a valid Lewis structure for this organic compound. So when we break this down, the rules for organic compounds are hydrogen has 1 bond. Carbon should have 4 bonds. Nitrogen should have 3 bonds and 1 lone pair. And oxygen typically has 2 bonds, 2 lone pairs, and any halogen, which we'll just call X, would have 1 bond and 3 lone pairs. So I'll actually start from the right and make this a little bit easier. But so N, H, H, lone pair, bond. So that must be connected with this carbon. So C, H, we've already accounted for 1, 2, 3, 4. And so this is 2 methyls. So 2 methyls can hook up there. 1, 2, 3. 1, 2, 3. This is a Lewis structure. That is a valid Lewis structure. It is good. If there is a space where one of these atoms does not have a bond, something to place it to, and there's a nearby atom without a bond, something to place it to, you can combine those 2 bonds into a double bond. So empty space right here and an empty space right here, and combine them together to get a double bond. Okay, what is the formal charges on chlorine and oxygen? Chlorine should have 7, oxygen should have 6. So all the oxygens are the same, so we can each oxygen we should have 6, and we have 1, 2, 3, 4, 5, 6, 7. So each oxygen has a -1 formal charge. Chlorine should have 7, and it has 1, 2, 3, 4. The formal charge of +3. Classify the following compounds as reactions as acid base, precipitation, or redox. So in this case, chloride, if you can find even one redox, it's redox. If you can find any one solid, it's probably precipitation. And if you can find, precipitation will be a double displacement that forms a solid. This is typically a double displacement that forms water. Anytime you see a charge. Well, so looking at the first one, even though you may or may not know this is the rare case where oxygen is not -2, you recognize this is 1-, and ClO 1- would have to be 1+, so that this is 1-. You can figure out, oh, okay, so this must be a redox. Zinc sulfate, potassium hydroxide forms zinc hydroxide and potassium sulfate. Let's look. So here's zinc. Here's hydroxide. That's a solid. Even though we have a base, that forms a solid. So that's a precipitation. We have NaOH, we have H3PO4. We form water. That's our acid base. And we have a pure element. A pure element forms this. Even though this guy is a traditional precipitation product, it is formed not through precipitation, but redox reaction. So there's number 20. Now, what rule of the valid Lewis structure does NO3 neutral break? So if you think about this, N is 5, O is 6 times 3, which is 18. And so 18 plus 5 is 23. There's an odd number of electrons. Odd number of electrons means this is going to have a radical. That's a radical. So if you draw this, you would draw something like this. 23, 1, 2, 3, 4, 5, 6. So I'm down to 17. 2, 4, 6, 8, 10, 12, 14, 16, 17. So, and to give nitrogen octet, you would have to put a double bond there. So we have a radical on one of the oxygens. And this guy ends up being +1, and that -1, and we have a radical. Now, what is the molecular geometry of the selected atoms? To do this, you just have to look at each atom individually. So this carbon has, scroll down. To do this, you have to look at each atom individually as a center atom. Carbon 1 has 4 electron domains. How many lone pairs does it have? 0 lone pairs. So what is the molecular geometry? Tetrahedral. This carbon has 1, 2, 3 things coming off it, 3 electron domains. How many of them are lone pairs? 0 lone pairs. All the lone pairs are on the oxygen. So what is its shape? It is trigonal planar. Now this oxygen has how many things coming off of it? 1, 2, 3, 4. 4 electron domains. But it's 2 lone pairs. So it's not tetrahedral, it is bent or angular. That's how you do it. This question, 23. which element in the following reaction is being oxidized? So which one is losing electrons? So you have to put a charge on all the atoms. H is +1. C would have to be -4. Oxygen as a group is, as an element, is 0. Oxygen in a compound is typically -2. So H stays +1. Carbon goes to from 4- to 4+. So which one of these atoms is being oxidized, thus losing electrons? Well, carbon is going from -4 to +4, so it's losing 8 electrons. So it would be carbon. Oxygen is going from 0 to -2, so it is gaining electrons. And hydrogen stays +1. Okay. Last page. Last two problems, in fact. Which of the following compounds are polar? Circle all that applies. So remember, equal and opposite cancel out. So this fluorine and this fluorine cancel out. But do this fluorine and this hydrogen cancel out? The answer is no. So this one is polar. We have 3 chlorines and 3 fluorines, but each of these guys are polar in itself. They do not cancel out. It's a non-polar shape, but because all the atoms are different, we have a bunch of polar bonds. Now here's a tricky one. We have a lot of polar atoms, but chlorine and chlorine cancel out. These 3 fluorines cancel each other out. So this is a non-polar molecule. And this one, even though it looks very polar, this is even though these bonds are polar, the shape is very non-polar. And because all the outer atoms are the same, they cancel each other out. So 1 and 2 are polar, 3 and 4 are not. Then finally, this was a trick question. Acetic acid, which is a weak acid, reacts with KOH. What is the equation? Even though acetic acid is aqueous, it is a weak electrolyte, and thus, when they swap over, it's going to play havoc on our answer. So liquid was then K acetate, C2H3O2. If you look at the solubility chart, you find acetate is always aqueous, as is K. So this is our equation. However, when we move down to the next step, to breaking it into the total ionic, even though this is aqueous, stays together. However, I'm not going to ask this right now because that is a tricky little bugger. So, H2O, liquid, and K plus aqueous, acetate aqueous. So our net ionic equation, all said and done, K plus cancels K plus, and that's all. That stays together. So acetic acid plus OH minus forms water and acetate. My bonus for that year was write your favorite science-related movie quote. So that was test 3. If you have any more questions, please send me an email. I'll be glad to try to answer them. But hopefully this will help you, especially considering those of you who were not able to make it to either this Friday's class or the coming Monday's class.